Hi viewers, welcome back to the series of lectures on mechanical vibration. Today we are going to look at something pretty simple but conceptually very important. It is the topic of connecting multiple springs in different ways. So mainly there are two ways in which springs are connected. Before coming to springs and masses and all those stuff, let me tell you, in vibration analysis, most of the real life objects will be modeled as mechanical model, discrete mechanical models for a preliminary analysis. So in that way, the springs and all these things, the discrete masses and dampers and are useful. Okay, just to drive home the relevance of these springs in the field of mechanical vibration. Okay, so one of the orientations or the ways in which the springs are arranged is like this. This particular arrangement is called series, and let's say there are two springs arranged in series. There are 3 points indeed, one second and the third. So there are 3 points and there are two springs connecting these 3 points. So the spring 1 is connecting point 1 and 2, and the spring 2 is spring 2 is connecting the point 1 and 2, and spring 1 is connecting the point 2 and 3. The whole Okay, now you know that two springs are there. What is the effective stiffness of the system? That is something what we are interested in. In order to evaluate that, we are thinking this whole arrangement can be replaced by one single spring, and let's say the stiffness of the spring is K nu, the new stiffness of the spring, and the same end conditions prevail. This particular end is fixed and this particular end corresponds to the point 3, and the whole system is acted upon by a force capital F. Make sense? So our goal is to figure out what is K nu. The very basic concept of this particular arrangement is that when you have springs in series, the force acting in each of these springs will be the same. I hope you understood it. That's because whatever force I am applying here, it will be transferred to K1, and the same amount of force will be transferred to K2. That is the key takeaway or the key take home that you need to remember when you have springs and series. Using that concept, now here I'm drawing the free body diagram of the two springs individually. Here I have drawn the free body diagram of spring 2, and here you can see the free body diagram of spring 1. So the spring 1 is having a net displacement of u3 minus u2, because this end is moving by an amount u3 and this particular end is moving by an amount u2. Just as you can see here, see this point is moving u2 and this point is moving u3. So the net displacement felt by this particular spring will be u3 minus u2. Extending a similar kind of explanation for the spring 2, the net displacement felt by this particular spring will be u2 minus u1. So using the aforesaid principles, we can write these two expressions simple: F equal to kx, nothing else. From this, what I'm trying to do is, let's say this is my equation 1 and this is my equation 2. In equation 1, I'm just introducing this particular mathematical jugglery or whatever you can say. I'm just adding this term. This term is u3 minus u3, which is 0. So I'm not modifying the equation much. I'm not at all modifying the equation, but I'm rearranging the terms in between among this, and then I'm bringing this particular term u3 minus u2 so that I can substitute for this u3 minus u2 from equation number 2. u3 minus u2 is F divided by K1. Okay, so this is just some mathematical cranking. That's it, nothing else. Finally, see, I have an expression like this. I have an expression F is equal to u3 minus u1 into this particular term over here. What is u3 minus u1? when you have a new system, new equivalent system, this is the equivalent system which we were talking about. I have a new spring, and the ends of the spring, the net deflection felt by this new spring will be u3 minus u1. So for this new spring, I can write this particular equation. Let's say this final equation was equation number 4, and this new equation is equation number 5. I'm writing equation 4 and 5 next to each other. Now we understand they're both similar. From this to comparing these two expressions, I know that new stiffness will be, or an equivalent stiffness of the spring system will be 1 by k1 plus 1 by k2. If you have n springs, this will continue like 1 by k1 plus 1 by k2 plus 1 by k3 up to 1 by kn. So that's it. So we derived the equation for equivalent stiffness when springs are arranged in series. Make sense? Now let's go to the next way how in which springs are normally arranged. Here also you can see the springs are arranged in parallel connection. The key concept or the key thing you should remember about parallel connection is that all the springs will experience the same amount of deflection. Here you can see spring 1 is undergoing a net displacement of u2 minus u1. u1 is fixed, but for generality, let's say the displacement seen by this spring is u2 minus u1, and the displacement seen by the second spring will be again the same u2 minus u1, and it is acted upon by an external force F as shown here. Again, our goal is to find out the effective spring, or let's say I am replacing this system with a new single spring system, then what should be the effective stiffness of that particular spring. For that, again we are starting with writing down the free body diagram of the spring. Here I have shown you this free body diagram of the two springs. As you can see here, the forces acting in the springs are no longer the same. But what is the same? The net deflection is same, but no longer the forces are same. So let's say the force acting in the spring 1 is F1 and the force acting in the spring is F2. And now how they will be related to the net external force that I am exerting here. Hold your thought and then come back. They should add to capital F. Both the forces, both the internal forces generated in the spring should add to the external force what we have applied. Putting that mathematically, here it is. F is equal to F1 plus F2. Now again simple mathematical substituting for F1 and F2 from the basic equation for a spring, we have this particular expression. Now if I want to change this particular system into a very single spring system, then this particular single spring should have a stiffness given by K equal to K effective, or the new K should be equal to the sum of K1 and K2. Makes sense? So let's conclude. When you have springs in series, the net stiffness is given by this particular formula over here, and when you have springs in when you have springs in parallel, they are simply given by the sum of the individual spring constants. Two remarks, this will be useful when you do problems. Let's say you have two springs in series arrangement, and the stiffness of one particular spring is K and the stiffness of the second spring is K by N, then the effective stiffness will be K by N plus 1. For example, you have a spring with 8 Newton per meter stiffness, and you have another spring 2 Newton per meter, another spring with a stiffness of 2 Newton per meter. Then if you are asked what will be the net stiffness if I connect these two springs and series, the answer is 8 by 5, because using the same formula you had 8 and 8 divided by 4 in series arrangement, so you should get effective stiffness of 8 by 5. So this is a useful trick which you can use when you are solving problem. And the other tricky question I have for you is this one. So let's say I have a system like this. Let's say there are two springs K1 with different stiffness, and there's a little m mass in the middle. They are connected like this. Let me ask you this question: what kind of arrangement is this? Whether this particular spring, whether these two springs are connected in series or parallel? In the first look, you may think that these two springs are connected in series, but you are wrong. These two springs are connected in parallel. Why? Because the deflection felt by the spring K1 and K2 are the same. I told you that's a key thing we should remember. If springs are connected in series, then the force acting in individual springs are the same, and if two springs are connected in parallel, the net deflection seen by the springs are the same. So in this case, the net deflection seen by the both of the springs are same, because if, let's say, if I move this particular mass by 2 mm in towards this side, then this will extend by 2 mm and this will get compressed by 2 mm. So the net deflection felt by the individual springs are the same, at least in the magnitude. So this particular connection falls under the category of parallel connection, and the net stiffness in the system should be the sum of the individual stiffnesses, which is nothing but k nu equal to k1 plus k2. Thanks for watching.